work with this. All right. So yeah, we spoke about last class the velocity time graph where velocity is on our y-axis and t is on our x-axis. When we see that there's a constant increase in the velocity of the object which is moving here, you would say that is basically accelerating. All right. So in this case, it started from zero, right? Started from zero and then it continues. And in this case, it started from, it was already moving. And then we'll call V0 our initial velocity. All right. And we said that the gradient of this velocity time graph for a motion constant acceleration gives us the value of the acceleration. That would be the gradient. And we solve that. So when you look over the notes, were there any concerns or any problems? Did you
No,
get a
sir.
chance to look over? Right? There were no problems. All right. Okay, now move on to instantaneous acceleration. Remember we spoke about instantaneous velocity. And what did we say instantaneous velocity is again? What did we say the meaning for instantaneous velocity? No one?
Sir, remember, sir.
All right. So instantaneous, what does instantaneous mean? Hmm. What does instantaneous mean? What do you think it means? Hmm?
Sir, like immediate.
All right, so immediate. Any other word?
It is done instantly, sir.
All right, so instantly. That's good. So that would mean at a particular instant or at a particular time, right? Hmm? A particular time. So we can find the average acceleration of the body using this graph. But what if we wanted the acceleration at this point? Say there was a change in, it was as constant as this one. Right? Say there were different changes, then we could find an instant acceleration, and that's what we'll do. But before we do that, instantaneous acceleration is the value of the average acceleration. It often differs in different intervals of time. All right. So the chances are a body is not moving like this because it will come across many obstacles. Right. For example, it slows down and so forth, or it goes around a curve, it will slow down, or will change direction. Therefore, the acceleration is different. No. Um, so therefore, the average acceleration often differs in different intervals of time. So it is useful to define instant acceleration, which is analogous to the instantaneous velocity discussed previously. All right. So instant acceleration. This is a very technical definition. Is the limit of the average velocity as the time intervals delta t goes to zero. All right. So as you will never find delta t being zero, but you find it going closer and closer to zero, meaning meaning that it will be so small, right? It is acceleration, but it will be so small that we call it zero. All right, so that's acceleration at a particular instant. It is so small, right? But we're not going to necessarily call it zero. It is a limit going towards zero. There's a limit of delta t going towards zero. See if you understand what I'm trying to say here. So here again, the notation limit delta t goes to zero means that the average of delta v over delta t, which would be our acceleration, is evaluated for smaller and smaller values of delta t. The closer delta t gets to zero, the closer the ratio gets to a fixed number, right? So this would be at a particular instant. All right, I know it sounds technical, but all we're trying to say for this slide is that, right, delta t is not zero. Delta t is going towards zero, right? It's not completely zero. If it was completely zero, right, what would be the acceleration? Say we had delta v over zero. What would this be? What's the answer for the acceleration? What would this be?
Zero.
Exactly. So delta t cannot be zero. It has to go towards zero. It has to be as small or going towards it as best as possible. Get it smaller and smaller. And therefore, we can find the difference in the acceleration, in the velocity, which would give us our um, acceleration. All right, so this is not possible, right? Delta t delta t cannot be equal to zero. So are we clear on this?
Yes, sir.
All right. So it's not really I would say you're not going to require to know about limits and so forth. This is just notation, right? Scientific notation just to prove a point, right? I think moving forward, you will be introduced to these in to limits further in mathematics. If you're doing integrated mathematics, I'm not sure about applied mathematics though, but you'll be introduced to limits. All we're saying is that delta t cannot be zero. But instantaneous acceleration, it should be at a particular point, so small, but never zero. All right, so motion with a uniform velocity a. All right, so um, what is the velocity of this object here? What is the velocity of this object? Hmm?
Zero.
Based on the graph. Hmm? I heard someone answer. No one. Are you seeing the screen here? All right, looks like my mic is not working. Let's see what is happening. Are you hear me?
Yes, sir.
Yes, sir.
All right. Um, are you seeing the screen now?
Yes, sir.
All right, good. So, what is the value of what is the accelerate? What is the value of the velocity here that this object is moving?
20 miles per second.
All right, so 20 meters, right?
Well, yes, sir.
Yeah, 20
Yes,
meters per
sir.
second. Now, is this object accelerating?
No.
No, no, sir.
Exactly. So it's not acceleration. Is everyone seeing that?
Yes, sir.
Yes, sir.
All right. Does anyone see that? Anyone disagree or anyone don't understand why it's not accelerating? All right. Right. So it's not accelerating. It is accelerating. It's moving constant. So it's moving over 5 seconds. We have one here, two here, three here, and four here. So over 5 seconds, it is at the same acceleration. So therefore, it is a uniform velocity. All right. So a motion with uniform velocity is a motion in which the body moves at steady speed in a steady direction. Remember, whenever we're talking about velocity, we're talking about the magnitude of the the speed or the how fast the object is moving, and also direction. Now, what happens if the direction changes? What will happen to the velocity? Will it increase? Will it change or will it stay constant?
Sorry, that changed.
Right, so it will change. Beautiful. All right, so velocity time graph for a uniform velocity motion. All right, so velocity on our y-axis and we have time on our x-axis. Figure below shows velocity time graph of our body moving at a speed of 20 meters per second for 5 seconds. Right? You should find the area under the graph. So what is the area under the graph? How do you find area here?
Gonna be 20 times
The
5,
area
sir.
of that particular graph.
Uh,
Go again.
20 times 5.
All right, so we see 20, right? 20, 20 times 5, right? And how much do we get?
100.
All right, so 100 meters. 100. Now, this 100 is the amount of distance that the object traveled, all right, over the 5 seconds. Now, tell me again, what is the, the, the formula for finding velocity with respect to?
Um,
Mhm.
I um, I distance over time.
All right, so V equal distance, which would be say S over time. Now, if you want to find the distance, how do you do that? What would be the next step? If you want to find S, what do you do here?
Transpose, sir.
Right? So transpose, correct? So how do you transpose?
Multiply both side by t, sir.
Multiply
Yeah,
both
so
sides
your
by t,
velocity time.
right? So multiply this side by t, multiply this side by t. I'm sorry, my stylus, I left it at home and currently at school. Right? I don't know why I managed to leave it. So this t cancels and this t cancels as well. Now we're left with s and v times t, right? Now, what does this look like? Doesn't this look like this right here? V times t. We're seeing that, right? Would give us s. Are we seeing that?
Yes, sir.
All right, so this would be 100 meters. All right. So in conclusion, the area under a velocity time graph is equal in value to the displacement of the body. All right, the displacement of the body. That would be how much the basically the distance between the initial position and the final position of that particular body. So the displacement time graph for a uniform velocity motion, right? Figure below shows the displacement of a body at intervals of time. Intervals of time. Um, so you should find the gradient of the graph. All right. So let's say we draw a line here, right, from the 10, and we draw another random line here from the 40, like someone has drawn. This is tricky. Let me see. Let's use this one that they have. All right, let's go back. Right, so let's use this one up here. 5 and 10. All right, this is our triangle. Now, what is the formula for finding the gradient of this graph? So let's start. M equal what?
Y2 minus Y1.
Minus
So
Y1.
what is y2? Which one is y2?
X2.
60.
Which one is y2?
50.
50, right? And y1 is how much?
10.
10 divided by which one is t2?
5.
5 minus which one is t1?
1.
All right, minus 1. And what we have at the top?
40.
40 over.
40
Over
over
4.
60.
And what's the final answer?
10.
Right, so 10. Right, and our units. What is our unit here? What we have at the top again? What is on the y-axis? What is on the y-axis?
Sir, meters per second.
Right, so
What's
meters
that?
per second. So meters at the top, so that's good. Meters at the top, and then we have seconds in here. The final thing, the meters per second. Anyone doesn't understand what is happening?
Me,
Alright.
sir. Just joining.
That is machine.
Yes, sir.
Alright, so no problem. We're just talking about the velocity time graph, and we said essentially that because this is the velocity and we have a straight line here, that's how we were saying the straight line here. Therefore, it means that the velocity doesn't change, so that means that there's no acceleration. So therefore, it is a uniform velocity. But this particular slide, we said that the area under the velocity time graph is equal. Question? Is that
No,
a
sir.
question?
Continue.
All right, so the area under the velocity time graph is equal in value to the displacement of the body. So we see that the object is not accelerating, but if we find the velocity and we multiply it by the time, which would give us the area, then we would get the total displacement of the object. That's all we were trying to say. All right. Okay, Oshi, that clear? Oshi, it seems she's not hearing me. Okay. So we moved on to this one, and we found the gradient of this particular graph, displacement um, versus time graph. And we said that if we find the gradient of this, it would be the meters or the displacement over time. And therefore, the gradient would give us the velocity. So V here would be equal to 10 meters per second, right? So are we all good here now?
Yes, sir.
Yes, sir.
All right. So, in conclusion, the gradient of the displacement time graph for a uniform motion is equal to the velocity of the body. So note that according to the last graph, for a uniform motion can also be defined as a motion in which the body covers equal distances equal distances in a straight line in equal intervals of time. Are we all seeing that it got equal distances? So let's say this is 20 times 1, right? Say the object is traveling um, from school to Chilani or school to Falmouth, right? It will, when it's traveling at 20 meters per second, it is able to go, right, cover the same distance in the same amount of time. All right. So let's look on this. If we take the area for this section here, okay, I think we're going too deep, but let's just look at this quickly, right? If we take the area for this section here, 20 times 1, how much you get,
20.
right? And then we see take the same thing again, 20 times 1, right? So we'll see that it will continuously cover 20 meters throughout the entire journey because it is going at the same velocity. If it was increasing now, then it would cover more distance over the interval of time. All right, that's what we want to accomplish for this slide. So, acceleration is going from place to place in your car. You rarely travel long distances at constant velocity. The velocity of the car increases when you step harder on the gas pedal and decreases when you apply the brakes. Right. So velocity also changes when you round a curve, alter your direction of motion, which we saw earlier, and as a result, we can say that acceleration is the rate of change of velocity. All right. So average acceleration, a car moves along a straight highway as in the figure below. I'll show the figure now. So this should be here. This is not a part of the um, not a part of our definition. Right. So acceleration. So a car moves along a straight highway as in the figure below. All right, so a car moving to the right accelerates from a velocity vi to a velocity of vf in a time interval delta t, which would be the change in the final velocity and the initial velocity. Therefore, the acceleration is equal to delta v over delta t, and our unit for acceleration is what exactly? Right?
Meters per second.
Exactly. So meters per second squared. Meters per second squared. The velocity for no, the unit for velocity v um, unit. I wish I had my pen. Unit meters per second. But for acceleration, we added one more change in time. So therefore, it is meters per second. So it would be basically s meters per second, and another second would be down here. So therefore, it would be equal to meters per second squared. Are we all seeing that?
Yes, sir.
All right. So on a velocity versus time graph, an object below illustrates this the slope of the line from this point to this point, right, would give us the acceleration. All right. We're not going to go too deep into this, but it's the same concept as our average velocity. Remember when we had this here, oh, here, right? And we said that the average velocity would be the slope of the graph from this point to this point. If you wanted to find the average velocity to say this is A, B, C, from A to C, you would draw a line from the beginning to C to get the average acceleration, average velocity. It's the same concept for acceleration. If you want to find the acceleration or the average acceleration of the body, right, as I said, it is constantly changing. In real life, you're not able to find the average acceleration by, or it is never a straight line. You'll never see that. It will always be a curve. But in order for us to find the average, you would take from the beginning point to the end point, and then you would find the gradient of that line, that particular line. So, are we clear on this, right? If you want to find the average acceleration, all right? Anyone not clear? Please let me know if you want me to go over it again. So I'll take it as everyone is clear. All right. Acceleration is a vector quantity, right? Why? Because of course velocity is a vector quantity. So therefore velocity is a part of acceleration. So therefore acceleration must also be a vector quantity. And the SI unit is meters per second or meters per second, right? And what we said this section is again? What is this section here?
Where is it, sir?
What is this section here?
Velocity.
Velocity, right? And if you further divide it by seconds, again, you would get acceleration. That's what we're trying to say for this particular slide. All right, so this section here is for velocity, but the entire thing is acceleration. So an average acceleration of 5 meters per second means that on average the car increases its velocity 5 meters per second every second. This should be 1. So it increases its velocity 5 meters per second every second. That's what we're trying to say for this slide. All right, and as we said earlier, if you want to find an instantaneous acceleration at P, you would draw a tangent to the line. Draw a tangent to the line, and then you would find the gradient of that particular line. All right. So in order for us to find the instantaneous acceleration at a particular point. All right. So the last thing before we close today, if we finish this in time, we'll go early. So this is the kinematics equation of the motion with uniform acceleration, right? Uniform acceleration means what? Is it changing or is it constant?
It is
Constant.
constant.
Exactly. All right. So if a body moves, that's how I want you to answer my other questions, right? Don't shy out on me, please. All right. So if a body moves at uniform acceleration, the velocity will increase uniformly, right? That is, the velocity of the object will increase by the same amount in equal intervals of time, right? So as you said, if there's an acceleration of 5 meters per second squared, it is an acceleration of 5 meters per second squared. The object will increase its velocity by 5 meters per second every second. That's what we're trying to get here. All right, so average velocity, right? If we have two velocities, we have an initial velocity and we have a final velocity, right? The average, of course, or the mean value, we would add both of them and then divide them by two, right? That would be for your average, right?
Right.
Okay, good. So if S is the displacement of the body in a time t, average velocity can be found by, we know this equation. We are already familiar with this. Was I recording this class? Yes, good. All right, so um, we know this equation, right?
Yes, sir.
Yes.
All right. Now, making an inequality from equations one and two, right? If we equate these, remember that this is v and this is also v. So v is equal to v. V equal to v. So we would say s over t is equal to the average velocity. Both of these are average velocities, right? So we would say s over t equal average velocity, right? Then we would multiply both sides by t. Are you hearing me? Or is that noise in the background bothering you?
Hearing you, sir.
Hearing, sir.
All right. All right. So if we multiply both sides by t, I'm sorry I don't have my stylus, right? So I had to. This is my notes. I wrote these down, but I had to scan them, right? I scanned them just in case something like this happens. So I scanned my notes and then upload them. So I wish I had my stylus to show you further, but it was a good thing that I actually scanned. I scanned all my notes. All right, so S is equal to V0 plus V over 2, right? So this is equal to 2, and you multiply both sides by T, right? Now, if we bring out this half, or we call it factorizing, if we factorize this half out of the equation, we will be left with half V0 plus V, right? Are we seeing that? If we take out this 2, are we seeing that? You're just left with V0 plus V. All right.
Yes, sir.
Exactly. No, in this case, right, we see an equation that we're familiar coming, right? But if V equal V0 plus AT, we would substitute in this particular V, and then we will get V0 plus AT. Right? Are you seeing that? Let me say it again.
Sir, I
So
understand when you say
S
the
is
signing.
equal to half V. Okay, good. Anyone not clear so far? Okay.
Sir, not clear with the
No,
V0 part,
because
sir.
are you clear with that? You say not clear
Yes, sir, not clear.
with which part? This part
Yes, sir.
with substituting, right? If we have S is equal to half V0 plus V times T, we would substitute in this V. This V and this particular V is the same thing. They are both the same. Remember, you know this equation, right? You have seen this equation before, right?
Right, sir.
Exactly. So if we plug in this V0, right, we would have V0 plus, if we plug in this V, we would be left with V0 plus AT. It's the same V. We can equate equations and plug them in, and we'll do that. So what we have been doing for the past week or so is the fundamentals. Now we'll be doing a lot more showing of equations, how we derive equations. All right. This is just like the first one. All right. So we have a couple more. So it would be good if you could practice showing this particular equation. So if you see on the exam, show S is equal to V0 plus minus AT squared over 2, right? You could show this because you would have practiced it from class. All right, so simply what we do here is we equate V0 plus AT and we place it in the equation here. Then the next step would be we see that we can add the two like terms here. We can add the two V0s together and we'd have 2 V0 plus AT multiplied by T. Now, if we take this 2 outside of the equation, right? Say we multiplied, we took it out earlier, but let's just say we expanded the equation and we multiplied both quantities here, V0 and AT by half, we would get this 2 V0 over 2. And say we also put the T in as well. We multiply both of these by T, so we multiply half by this one and also half by this one. Expanded equations from mathematics. And we also set T times that and T by that. Right? We would have S equal to 2 V0T over 2 plus AT squared over 2. All right, let's think for a second. So all we're doing here is expanding the equation. So we equated V equal V0 plus AT. Now we'll go ahead and expand it. So are we seeing this step here, this particular step? Are we seeing that?
Yes, sir.
Or anyone not seeing that? All right. So the next step then would be to simplify. Now, T times T is of course T squared, and then we bring down the A, and because we multiply by a half, we multiply both of them by a half. Or let's just say we divide both of them by 2. We would have 2 V0T over 2 plus AT squared over 2. And the final thing, we would cancel these two. These two would cancel each other, right? And then you could bring down your AT squared. So we'll be left with the final thing as V0T plus AT squared over 2. All right, are we good? This is the last thing for today, right? Are we okay here? Just one more slide after this.
Sir.
Question?
No, sir.
Okay. Good. All right, so we just basically bring over this equation again. S equal V0t plus AT squared over 2. No, this is the displacement of a body undergoing uniform acceleration, right? This is the displacement of a body undergoing uniform acceleration. So the A doesn't change. If the A changes, then this formula is not applicable. If the A changes, then this formula is not applicable at all. Because the A is constant, right? You find out that it is applicable. Now, if V0, what if V0 is equal to 0? What will happen to this? What will happen to this side? If V0 is equal to 0.
And that side would be 0, sir.
Exactly. So we would be left with S equal AT squared over 2, right?
Yes, sir.
All right.
Yes, sir.
So that is in the case v0 is equal to 0. So say v0 is our initial velocity, and if the body started at rest, then v0 would be 0, and then it accelerated by a constant velocity, by a constant acceleration, right? It accelerated constantly. Then we'll be able to find how much ground or the displacement of that particular um, of that particular object. Now you can see here from a displacement versus time graph, right? What does this indicate again? I want you to remind me. What does this straight line indicate?
Constant
Constant what?
acceleration.
Continue.
No.
No.
Uh, I heard
The
something
velocity,
say it.
sir.
Exactly. So this on a displacement time graph, it is velocity. But on a velocity time graph, the straight line means what?
Sir, the acceleration now.
Right, this is acceleration. So this is acceleration and this is your velocity. Just to be clear. No, on a displacement time graph, you have a curve. What does this indicate?
Um, in a constant.
Exactly. So the velocity is not constant here. The velocity is changing. So therefore, the object is not covering the same amount of ground in the time. It is constantly changing. It is not constantly changing, but it is changing. That curve is suggesting that it's changing. In this particular case, it is constant, right? So we end up with a graph looking like this. And if we had t squared, right, instead of t, we don't have a straight line because s and t are inverse or directly proportional. Which one of them? S and t. Are they directly proportional or are they inversely proportional?
Inverse, sir.
No. Again, as s increases, what happens to t squared?
The time increase.
Increase.
Exactly, because they're in the same line. All right, so it's just these little things. That's why we had to go over that week, right, of preparation, get your mind back to CSEC, right? Get your mind up and running again, alert. If we have S here and T squared, as S increases or as T squared increases, the other one increases. So we see this in the graph here. As t squared increases, there's an increase in our displacement. All right. Um, are we good?
Yes,
Understand?
sir.
Yes, sir.
All right. So as you get a chance, read over your notes. All right. Very important. I will upload these now. I will upload these now. Read over your notes as I get the chance. Very important. We'll do the activity on. We'll do the activity together on. I mean tomorrow. Tomorrow is our next class. Yeah. So we'll do the activity together tomorrow. Let's see how far we can reach for this week.
What's there tomorrow? We're not gonna one.
Right. Right. You're gonna be at school. So,
Mm.
all right. For the second session, I am going to send you. You'll be home. You should be home by 1 o'clock tomorrow. I think. All right. So I'll give you a homework tomorrow. Okay. Yeah. I'll give you a homework tomorrow. To complete for Friday. All right. Ensure that you read over your notes. Very important. Because if you don't, you take it for granted. Oh, Mr. Treasurer provide the notes. I don't have to write any notes. Then for the time of the exam, all right, you're gonna be stressed out. All right. So take the time now. If you have any free time, just read over. All right. Okay.
All right, sir.
All right. All the best,
Yes,
brother.
sir.